Hey guys, Junkie to Monkey here. Today we're going to be talking about elementary operations. These things are specific to the architecture that you're on, whether that's an Intel processor, an AMD processor, 64-bit versus 32. But in essence, the basic operations relatively are the same across all of them. So today we're going to talk about the different things that you can do with those bits and bytes, why they're relevant, and why we need them. We're not going to spend a whole lot more time describing it, so let's just go on and get into it. Now, at the architecture level, from a CPU perspective, there are many different things that you can do. But it really all boils down to a couple different things, and so we're going to group our talk into a couple different scenarios, trying to keep things fairly simple. The first thing that you can do is that you can define a variable. Now, you define a variable as a set of bytes, and they're, again, based on the architecture, it's going to depend, but essentially, a variable boils down to something that holds some kind of value. We can define a variable. So we'll just make a little list here. We'll say define a variable. The second thing that we can do is we can perform some kind of arithmetic operation or some kind of arithmetic instruction. So we can do some kind of calculation. The third thing we can do is we can read a value from memory. And memory is stored in a couple different places. We'll talk about that later. Or we can write a value to memory. 5, we can perform a logical check. And 6, we can now, in a computer application, a lot of the time you're going to have things that change throughout the course of the application running. You may have the user input some value. You may have a value coming from a database somewhere. You may have something happening in a game application that causes something else to change. And you need a place where you can store those things and reference those things that can change but still give you the same handle. So in the case of an algebraic equation, we'll just use this as a really simple example. We could say something like 2 times some value a equals 8, right? Well, we obviously know what the value of a is here, but in this particular scenario, a is our variable. Now, this can't really change very much, but let's say that in the case of 2 times a equals some value in, we could say that this is a function of, say, 2, right? And when we substitute 2 in for a, then in would be equal to 4. But we could also say, what if this is 5? Well, when we substitute 5 in for a, now we get a completely different value. And ultimately, this a is remaining the same. So it's always 2 times a. And we can reference a. And if I say a, you guys know what I'm referring to. The reason that this is so valuable is because because we've made that association, I know this name, this arbitrary name A means something, and you know it means something, and so we can converse about the fact that this thing is some value that can change at any point. So I've taken that table and I've moved it up to the corner, but let's first talk about variables. So as I said previously, you will want to store some changing value at some point in your computer application, and you do that by defining a variable. Every language does it a little bit different. In essence, what happens is you define something that has a name and generally a type. Now, this depends on the language, but generally you define a type and a variable name, and then you assign it some value. In this case, maybe we assign variable A to 1. Now, this could be a number of different things. It could also be something called a character, and we'll talk more about types later. But in this particular case, maybe we define the variable B to the value B. And this can change at any point. So later on, we could say, well, we want B to actually equal foo. And ultimately, the variable always remains the same. So I can have any number of values associated to it set by my application, but I always have a reference to this variable B. All right. So the second thing that we can do in our little list is arithmetic. All right. So we can tell the computer system to perform some operation. So we could say 8 times 4, right? And that would return some value. We could say, hey, like we had that variable A, I want this to be assigned to the value 2 times 6. And then in this particular case, now A would be equal to 12. So this is another one of those operations that a computer system has an instruction for, allowing you to perform some operation. You could also do much more complicated operations in arithmetic. So you can add, you can subtract, you can multiply, which is symbolized by an asterisk in most software languages. You could do division, which is often symbolized as the /. You could raise something to a power, which is the little caret. You could perform a modulus operator, which is oftentimes the percentage symbol. But all of it boils down to performing some kind of arithmetic operation. And we'll talk more about this once we get into actually writing code, and we'll explain what we're doing when we're doing that. But this is another example. You can perform some sort of arithmetic operation as an instruction to the computer system. The next thing that you can do, because we're going to kind of skip over some of these other pieces for a minute, we are going to skip over read and writing from memory for a second, and we're going to jump over to performing a logical check. So you can perform some kind of logical check. And what this means is you're saying something like, if 10 is greater than 9, then do something in here, else do something in here. Now, this is particularly powerful if we combine this with our variables. So we could say if A is greater than 9, then do this. And essentially, there are a couple different logical checks that you can do. You can say your typical like greater than or less than. You could also do an or check. So if the value A is greater than 0 or is greater than 9, or so if our value A is greater than 9 or some value B is less than 7, just as an example, then do some set of operations. So or is another option. You can also perform a logical check saying something is equal to something else, right? So we could say if A is equal to 9, you could also say not equal. So if A is not equal to 9, then we want to do something. And then there are several bitwise operators that you can do as well, which again we'll talk about later. But ultimately, in its simplest forms, these are the base level logical check operators. And then finally, we want to talk about loops before we get back into the memory stuff. So there are going to be times where you want to perform something many times. So in the case of our variable, say that A is equal to 1, and then we want to do a number of checks in succession. So combining our variables with our logical operations, we might want to do something like if A is greater than 0, then assign A to 3, else assign A to -3. And in this is going to create, in a looping scenario, something called an infinite loop. But we would want to say we want to perform this like many times, because the first time it runs through, we want it to set it to 3, and then the second time we wanted to set it maybe to -3. And again, in this scenario, that wouldn't work, but there are going to be cases where we want to do that, and you do that based on a loop. So we'd say, and this isn't real code yet, but I'm just going to say loop if, and then it's going to perform this until the loop is ended. And as an example, we could say we want to end the loop if A is less than, say, 0. Alright, so we skipped over memory for a little while because the other operations that you can perform are fairly intuitive. Memory is something that we need to understand pretty thoroughly. So let's just draw a little table here. So I've got a little table here, and I'm just going to create a series of boxes. Now we said that we can do two things in memory. We can either read a value or write a value. It's important for us to understand how memory is laid out in order to understand what we're doing when we're reading and writing. So whenever we define a variable or whenever we set a value, it's always put into memory. Now we can imagine memory as a table of slots. So think back to your PlayStation days and how you would insert a memory card into a memory card slot, and you generally have two of them, and then you could write things to that memory card slot. In your computer systems, it's operating very similarly. It has a giant table, although it has many slots, and those slots are allocated and can be requested to be written to or read from. So, as an example, let's just change our color value here. And let's say that we want to read the value in slot 48 here. And let's just assume for a second that the current value in slot 48 here is 100. We could make the operation read from memory location 48, and that would return us the value 100. Okay. We could also say write to position 10 the value 8, and then the operating system would allocate in memory slot 10 the value 8. Now, this is actually going to be referred to in binary. So it's not going to be stored in the memory system as 8. It's actually going to be stored as the binary value 8. But just for intuitive purposes, we're writing it like this. And essentially, because of the way that memory works in this kind of table format, requesting a value from a memory location or writing to a value to a memory location works very similarly to this. Now, you'd have to know what the memory location was, which is where things like variables really come in handy. Because whenever I define, like we did before, our value a as 1, we're defining this variable. The operating system is going out and saying, okay, where do I have available space to put that variable a? And let's say in this scenario that it decided that it wanted to put it at 4. Now, whenever we assign a value to the variable a, say we decided to set that to 5, this variable a is actually pointing to that memory slot number 4. So when we say A, the computer system is actually saying memory slot 4. And so when we assign this value, we're making that instruction to set or write a value. This A symbol is actually pointing to memory location 4. So if we think about it, A is synonymous in the computer system to whatever that memory location is. And this actually creates an interesting situation because there are actually two types of things that you can interact with. You can actually interact with the memory location, and you can actually interact with the value at that memory location. When we refer to the memory location, we call that a pointer. Now, a lot of the higher level languages don't actually allow you to interact with pointers, but a lot of the lower level languages, things like C and C++ as an example, do allow you to interact with pointers. The way that you would symbolize that just really quick, and we'll get into this again later, as you want to reference the memory location, is by denoting it as a pointer. So if we were to say pointer A equals the reference to A, then anytime we interact with this thing now, it's actually interacting with the memory location. So what we could do is we could actually say, hey, we want A to be the pointer A. We want that to point to the memory location of say some value b. And when we do that, and this is actually supposed to be an ampersand, just so that we're being clear here, I just can't write an ampersand. But we can actually interact with setting either the memory location of a variable, or we can interact with setting the value of a variable. And again, we'll talk about more on this topic when we talk about lower level systems, memory management systems. But just suffice it to say right now, just remember that whenever you're reading or writing a value from memory, the computer system is actually referencing whatever it is that you're writing and choosing a memory location to go and read that value from. Now, this gets a little bit more interesting too when we start talking about primitive types. So we keep using this type of int, which is a primitive type in most languages. There are also a lot more of these, and so it becomes a lot more interesting when we start discussing types, primitive types, and more complex types, and actually how much space they're taking up in memory. But at the end of the day, we assign or read from a memory value, and that is an instruction that we can perform inside of a computer system. So, anytime that you're thinking about what you're doing with variables or the operations that you're performing in your application, you should really make sure to refer back to how memory is being allocated and retrieved in your computer system. And you can really boil it down to a very simple table like this, even though modern computer systems are much, much bigger, have many, many, many more slots. Just knowing this interaction here will actually help you understand and troubleshoot applications that you're building. And finally, there's one more thing that I should mention before we move on to another topic on memory. So, memory is allocated in two different tables, actually. The first one is called the stack, and the second one is called the heap. And we will again talk about this much more when we're talking about the actual systems, memory management systems and such. But essentially, when you're allocating variables or object values, you're assigning things to the stack when you're doing things that rarely change, right? So more static type values or static references. Now, there is a memory limitation on the amount of memory available in the stack, and we'll talk about that later. But that's the basic reference there. And then when you're referring to the heap, you're referring to things that are created dynamically. And this is really where pointers come into play. So generally, when you're dealing with pointers, you're actually dealing with heap memory. And that's basically it for a high-level understanding of memory systems. This also concludes our discussion at a high level on elementary operations that you can perform on a computer system. We will definitely discuss more on this as we move forward in the course, but I'm hoping that everything is clear here as far as what variables are, what operations I can perform in reference to the computer applications that we're writing. So I appreciate you guys jumping in. I appreciate you guys sitting here through this with me, and I'm excited to see what we do from here. I also make sure that you guys are commenting, liking, and subscribing. Make sure to give me feedback, so what you liked, what you didn't like, so that we can make sure to improve the series as we go along here. In fact, there are already several suggestions that I've gotten that may require me to go back and redo some of the previous videos to make it more accessible to each one of you guys. So I appreciate you guys all tuning in and joining us for this lesson. In the next lesson, we will actually be talking about something much more relevant to actually building computer applications. And the next topic that we'll be discussing will be intermediate and operative systems. So this is where we're really going to, as I said in previous lessons, we're talking about things kind of in a building fashion. So initially we talked about circuitry, that moved us into binary moved us into elementary operations, and from there, now we're going to be moving into intermediate and operative systems, so things like memory management. Because we talked about the elementary operations, now we have a firm basis for moving into that lesson. So I'm excited to get to that. Thanks for watching. We'll see you next time.